Okay, but we're going to take a little break from finding areas under curves. We still do have one more video about that, but we need to take a look at sigma notation. Now, you might have covered this before, but I need to make sure everyone knows this, so we'll go through it today. Sigma notation. What is this all about? Well, first of all, the word sigma is the uppercase letter S in Greek, and it stands for sum. So when we're talking about sigma notation, we're talking about addition. We're doing a lot of addition here. So it looks pretty nice and fancy, impressive when you're doing stuff like this, but it's not so complicated really. Basically, the number at the bottom here where it says n equals 1, this is called the index. And this shows where the summation starts. And then the top number, in this case the 4, this shows where the summation stops. So for this first question here, we're starting at the number 1 and we're going up to 4. And what do we do in each case? Well, nothing. We're just writing the number down. So first of all, this 1 goes in the end position, 1. Plus, we add the next number. Well, after 1 comes 2. Plus, we add the next number, 3. When are we going to stop doing this? We're going to stop when we get to 4. And here we go. This is what this summation, this sigma notation here, this is what this means. So we're adding 1 plus 2 plus 3 plus 4. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. That is our answer in this case. Okay, how about this one? We're not starting at 1, we're starting at 2 this time. So 2 plus, wait a minute, it doesn't just say n this time, it says n squared. So when you plop the number in there, you also need to square it. So we're going to go 2 squared plus, lots of summing in this, 2 squared plus, well, we go to the next number up, which is 3, and we got to square it again, 3 squared, plus, next number up is 4, and we square it again, 4 squared. When do we stop? When we get all the way up to 6. So 5 squared plus 6 squared. And we can now solve the question. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. So let's see if I can add those quickly. 4 and 36 make 40. 9 and 16 is 25, and another 25 is 50, and 50 and 40 is 90. Take a calculator if you need it, but it will add up to 90 when you do it. Alright, the next one, a little bit more confusing. You're starting at 1 and only going to 3, so you're not going very far. So you're plopping the 1 in where the I is, right? Before it said n, and then you had n over here. Now you have I, starting at I, so you better have i's up over here as well. And you do. So where you see I, you're putting the first number, which is 1. But wait a minute, in brackets you have another I, so you got to put the 1 again. 1 plus 1. Okay, that's the first term, so to speak. Now you're going to add, this is summation, so you're adding. So we go to the next number, which is 2. So 2 goes at the start, in front of the bracket, and 2 also goes in the bracket, 2 plus 1. We got to do it one more time because we got to get up to 3. So 3 goes outside the bracket and also inside the bracket. 3 and then 3 plus 1. So what does that mean? We have 1 times 2, which is 2. We have 2 times 3, which is 6. And we have 3 times 4, which is 12. And if you add those up, you get 20. Alright, so if we were going to summarize, how does this look in mathematical terms? So this right here is kind of a general form of sigma notation. You would start at 1 here, so it'd be a to the 1. Then you would add a to the 2, second term, a to the 3. And how long would you keep doing that? You would keep doing that until you got a to the n, and you'd be done. And this, what we've just done here, this is called expanded notation. Okay, so the first thing we're going to do here is we're going to write these statements, these addition statements. We're going to write it using sigma notation. So we're going to write it using this. So when you see this, you might think that you start by saying n equals or k equals 1/2. And that's possible, but let's look for a pattern here. You see the pattern is that if you look at the numerators, it goes 1, 2, 3, I assume it goes 4, 5, 6, 7, 8, 9, 10, 11, 12, and on the bottom, 2, 3, 4, 5, 6, 7. Oh, so the denominator is always 1 more than the numerator. Why don't we do this? Why don't we put k equals 1 So because we have k here, we have to have k's in our expression here. In the numerator, if we put k on top, that'll work for the first term, right? If we put 1 to the k, yep, we got our numerator of 1. But we need to do one more of that in the bottom, so we'll put k plus 1 on the bottom. So let's just check the first few terms, make sure it works. If we put 1 in here, you get 1 over 2, yep. If you put 2 in here, you get 2 over 3, yep. If you put 3 in here, you get 3 over 4, yep, it works. It works all the way up to the last term. What's our last term? We want the k to be 12. We want our last term to be 12 there. And that'll work. That's it. Finished. Okay, another one here. Oh, I'm not so good at drawing these sigma signs. So let's start with k equals again. Now, what's the pattern this time? It looks like we have 2, 4, 8. Oh, we're multiplying by 2 every time. And on the bottom, 3, 9, 27, we're multiplying by 3 every time. So in effect, you're multiplying 2/3 and another 2/3 equals 4/9, and another 2/3 equals 8/27. It looks like we're multiplying 2/3 by itself a certain number of times. So why don't we say that we're going to raise 2/3 to the k power, and we'll start at k equals 1, because 2/3 to the 1 is 2/3. 2/3 squared is 4/9. 2/3 cubed is 8/27. Looks like we're doing a good job. We have to get all the way up to 2/3 to the nth power. Well, in other words, we want this k to be n. That's our finishing term right there. Okay, bit of a strange one, but there you go. Now, to be honest, if you're confused by this isn't actually a big deal with what we're going to do in calculus. What's more important in calculus is this next page here. So let's make sure we understand this. A couple properties of these summations. First of all, if you're summing and this bit here has a binomial or a polynomial into it, you can break it down into summation of the first term plus the summation of the second. Or if it was a minus sign, you could put a minus sign right there. But you can treat each piece one at a time with individual summations. I'll show you what I mean in this first example. In fact, why don't I do it right now? So you don't need to do this. If you wanted to, you could plug 1 into here. In fact, maybe I'll do this. But I want to show you that the other way you can do it is you can break it apart. You could look at the summation from 1 to 4 of k squared, take away the summation from 1 to 4 of 5k. And this will work. So let's do this. In the first one, the first summation here, we're going to start at 1 and go to 4. So we put 1 here and get 1 squared, plus put 2 there, get 2 squared, put 3 there, get 3 squared, and put 4 squared, or 4 there and get 4 squared, sorry. Let's put all that in brackets, because then we're going to subtract, and in brackets I'm now going to do this. I'm again going from 1 to 4, and it's 5k. So I put 1 in there, and I get 5 times 1, which is 5. I think I'll just do this here. Plus, I put 2 in there, 5 times 2 is 10. 3 in there, 5 times 3 is 15. And 4 in there to finish off, 5 times 4 is 20. So now I've got to simplify. 1 plus 4 plus 9 plus 16 minus, might as well do this right now. 5 and 15 is 20, another 20 is 40, and 10 is 50. Now I got to add this. 1 and 9 is 10, 26, 30. So I get 30 minus 50. So my answer is negative 20. Now, just to be clear, I didn't need to do that. I could have gone straight from here. I could have put 1 in here and gotten 1 squared minus 5 times 1 is 5. That would be our first term. Plus, put 2 in here. 2 squared minus 5 times 2 is 10. Plus, put 3 in there. 3 squared minus 5 times 3 is 15. And then plus, put 4 in there. 4 squared minus 5 times 4 is 20. And if I do this, I'm going to get the same amount. 1 squared is 1. Take away 5 is negative 4. I'm sorry, this is a bit of a mess here. Plus, 2 squared is 4. Take away 10 is negative 6. 3 squared is 9. Take away 15 is another negative 6. And 4 squared is 16. Take away 20 is negative 4. Negative 4 plus negative 6 is negative 10. plus, I guess I should actually have plus -6 is negative 16, and plus -4 is negative 20. You get the same thing, okay, as we had before. So you don't need to do this, breaking into two different sigma notations, but you can, and sometimes it's very helpful to do so. Okay, the second property right here looks like this. If you have a constant in this piece here, you can move the constant out front. So in this example, you can see I have this 6k. I could move the 6 out front. So I could actually answer, move the 6 there, find what the summation is from 4 to 7 of just k, because I've moved the 6 out front. So how would I do that? Well, I'm going 6 times whatever I do next. I put 4 in there, plus I put 5 in there, plus I put 6 in there, plus I put 7 in there, and that's the end. So 6 times 6 from 4 is 10, plus 5 is 15, plus 7 is 22, and when you multiply that, you get 132. Again, not necessary. I could have put 4 in here, 6 times 4 is 24, plus put 5 in there, 6 times 5 is 30, plus put 6 in here, 6 times 6 is 36, plus put 7 in here, 6 times 7 is 42. If I add those together, 54, 60, 90 plus 42 is 132. You get exactly the same. Okay, so useful properties, but not essential sometimes. Okay, here is actually the thing you'll probably use the most in calculus in the next section, is we have some formulas. If you only have a constant here, then the final answer is just going to be equal to c times n. Why would that be? Well, we just said that c could move up front. So basically what we'd be left with is c and then k equals 1, have our n there, and what would be left here? If we move the c out front, we just have 1 there. Now, since it's just 1 here, when you go to plug these numbers in there, there's nothing to plug in. You just get another 1 and another 1. Every single time you go from 1 up to n, you just get 1 plus 1. Basically what you're getting here is 1 plus 1 plus 1 plus 1, all the way up to n. You have to get n number of them, and then you're going to multiply it by c. Okay, if you start at 1 and go to n, and you're just adding up each number, 1 plus 2 plus 3 plus 4 plus 5, all the way up to n, here's two different ways of thinking of it. You can get the sum by going n times n plus 1 divided by 2. You can also, look, if you expand that, n squared plus n over 2. So those will be useful at times. If you do the same thing, go from 1 to n, but you have k squared, you get n times n plus 1 times 2n plus 1 over 6. And if you multiply that all out, you'd have to maybe start by multiplying these two, get a binomial, n squared plus n, and then multiply that binomial times this binomial. You'll get this, 2n cubed plus 3n squared plus n. So sometimes this will be more useful, sometimes this will be more useful. And finally, if you have k cubed, you end up with these three expressions which are equal to each other. So you'll decide which one will be easiest for you. Alright, so let's take a look. You can see I have one of each type. The first one is just a constant. I'm going from 1 to 10, and I just have a constant here. So what does it equal? Well, according to this first one up here, what it equals is the constant, which is 4, times n, the number on top, which is 10, so it's 4 times 10, or 40. So that one's not bad. Okay, the next one, we're using this one this time. So we're going from 1 to 15, and we just have k here. You can use either of these you want. It doesn't matter. I'll go with the first one. So we'd have 15 times 15 plus 1, which is 16, and then divided by 2. You could do the division first. 16 divided by 2 is 8, so you're going 15 times 8, which is 120. Okay, that's it for that one. Now we have an example that goes with this. We have a k squared. So you're going from 1 to 12. You can use in any of these you want. I think, again, I would probably use this first one here. So I would have n, which is 12. The top number is 12. I'd multiply it times 12 plus 1, which is 13. And I'd multiply that by 2 times 12, 24, plus 1, which is 25. And then you're dividing that by 6. So you could divide again the 12 and the 6. This would become a 1, and this would become a 2. So we got to go 2 times 13 times 25. Well, look, 2 times 25 is 50, and 50 times 13, Well, 100 times 13 is 1300, and this is half as much, 650. No problem. Get the calculators out if you want, but 650 is your answer. All right, finally we're doing the last one down here. So we're going from 1 to 19. My goodness. Again, you can use whichever of these you want. I don't really want to go 19 to the 4th power or even 19 squared, so I think I'll use the first one right here. So I'm going to go 19 times 19 plus 1, which is 20. I'm going to divide that by 2 and then square all that. So simplify, cancel this out, you get a 10. So you end up with 19 times 10, which is 190. Uh-oh, I think my streak ends right here. And you're going to square it. What's 19 squared? 391 or 361? 361, right? So 19 squared is 361, and then you add 2 zeros, so that'd be your answer. Just use a calculator. 36,100. All right, so there's a quick, hopefully quick, summary of summation, and we'll be using that next time when we figure out exactly the area under curves. See you then.